commutative group and non-commutative group. So we'll start from question 6. But before that, we will recall some basic facts. So here our recall 1. Let G be a non-empty set and not be a binary operation. Be a binary operation on G, then G with this operation is called group. If it satisfies the following condition. If and only the first one is A not B belongs to G. For all AB belongs to G, this property is called closure. Next, associative A not B not C, that will be A not B not C. For all ABC belongs to G. And third, there exists an element E belongs to G such that A not E equals to E not A equals to A for all A belongs to G. And next one is the existence of inverse. That means for all A belongs to G, there exists an element B belongs to G such that A not B equals to B not A equals to the identity. And here the identity element and inverse both are basically unique. If inverse exists, that will be unique. If identity element exists, so that is also unique. So now start the problem, important problem. So this is our question number 6, and that is asked in the year of 2003, and this is also important in other university examination. Okay, so here let is, this is equals to all the ordered pair AB such that A not equals to 0 and the first component is non-zero and both are basically real number, and the operation not is defined by A not B, A comma B not C comma D. This is basically AC comma BC plus D. Show that S naught is a group. S with this operation not is a group. This composition, this is group. And next question is it commutative? So for group, what we have to show? We have to show it is closure associative. There is existence of inverse and existence of identity. So here the marks is given 4 plus 1. So what is exactly given? It is given the set S equals to all this ordered pair AB such that A is non-zero real number and B is a real number, and the operation not, the composition, binary composition not is defined on S by A comma B not C comma D. This is AC comma BC plus D. Okay, so for all AB comma C comma D belongs to S. So what we have to show? We have to show that S naught is group. So we have to show that S with this operation not, this is our group. That we have to show. So that means first we will show the closure property. Next we will show associative. So first we will show it is closure or not closure. So for closure property, what we will take? We will take two arbitrary element AB comma CD belongs to S. So since AB comma CD belongs to S, then if we compose this to AB not CD, so that will be AC plus comma BC plus D. So and that is also belongs to S. Why? Because AB and CD belongs to S. So obviously A not equals to 0 and C not equals to 0, as A comma B comma C comma D belongs to S, and that implies AC non-zero. And obviously, and also AC is real number, C is real number, and AC must be a real number, and BC plus D all are also basically real number. Because here then we can write A non-zero, C non-zero, and A, B, C, D all are basically real number. Now, so obviously AB composed CD, that is obviously belongs to S. So what we have shown here, AB composed CD belongs to S for all AB comma CD belongs to S. Why? Because since AB comma CD belongs to S, that element are basically arbitrary element. Arbitrary. Okay. So closure property holds. Now we'll come to next important property, which is associativity. Associativity. So we'll take three elements. Let A, B, C, D, comma EF. So three elements belongs to S. Then first A, B, not C, D, and not EF. So A, B, not C, D, by the definition of the composition, that will be AC, comma BC plus D, not EF, and that will be AC means here AC multiply, so ACE, and BC plus D, here B means BC plus D, so BC plus D multiple F, so here BC, now so it will be E plus F. So that means it will be ACE, comma BCE plus D plus F. D plus F. Now, and we will calculate here AB naught, CD naught EF, and it will be AB naught, and that will be CE, and here you will see AB naught CD will be AC, comma BC plus D. So first, so that means D plus F, D plus F, and that will be ACE plus, comma BCE plus D plus F, D plus F. So that means again we get the same result here. So that means what we can say, AB not CD not EF, that will be exactly equal to AB not C not CD not EF, and that will be holds for all AB, CD and EF belongs to S, because these elements are arbitrary, so associativity holds. Now we come to the third point, that means existence of identity. So here clearly we can say that element 1, 0 belongs to S, because the first component is non-zero, and since 1 is non-zero and 1 and 0 both are real number, 1 and 0 both are real numbers, so it must be belongs to S. And we see that if we take any element AB composed 1, 0, So that will be A into 1 plus B into 1 plus 0. B into 1 plus 0. So into 1. So that will be, that is equals to A comma B. And again 1 comma 0, not AB. This is again 1 into A and 1 into 0 into A plus B. 0 into A plus B. Again it will be A comma B. And that is holds for all AB belongs to S. So that means 1 0 belongs to S is the identity element. So identity element exists. Now we come to the next important property. This is related to existence of inverse. This is related to existence of identity. Okay. So for inverse, what we will do, we shall show that, say here, let we have taken an arbitrary element, AB belongs to S. So then obviously A is non-zero and A and B both are real number. And since A is non-zero, so that implies 1 by A is also non-zero and minus B by A is also non-zero. And both are 1 by A and 1 by A is non-zero and minus and 1 by A comma minus B by A both are belongs to real number. That we can say. So now just we'll check and hence we can say 1 by A comma minus B by A, that is belongs to S. Now we check AB not 1 by A comma minus B by A. What will the value? A into 1 by A comma B.Sc, that means B into 1 by A plus minus B by A, and that will be 1 0. That will be 1 0. And also you will check 1 by A minus B by A, not AB. Again it will be 1 by A into A comma minus B by A into A plus B, according to the definition of composition. So what will happen? Again it will be 1 comma 0. So that means what we get? We get here AB not 1 by A minus B by A and 1 by A minus B by A not AB, and it will be 1 0. That means identity element. So that means, that implies 1 by A comma minus B by A, this element belongs to S, is the inverse of the element AB belongs to S. So we can say every element in S must have an inverse. That we can say. So all the property, closure, associative, existence of identity inverse, all are holds. So what we conclude? We conclude is with this operation not, this composition is a group. So the first part is done. Now we'll move to the second part. Second part, we will check it is commutative or not. Okay, so here S and not is defined by in that way A comma B, not C comma D. This will be AC comma BC plus D for all AB CD belongs to S. So we'll show that it is commutative or not. Okay, we'll see it is not commutative. The question is the group commutative? Our answer is no. This group, the group is not commutative. The group is not commutative. Why it is not commutative? Because for, if we take 1, 2, comma 3, 4 belongs to S, both are belongs to S, we have what we have 1, 2, not 3, 4. This is basically 1 into 3, comma 2 into 3 plus 4. So that means it will be 3, comma 10. And 3, 4, not 1, 2. This is basically 3 into 1, comma 4 into 1 plus 2. And this is basically 3, comma 6. So what we have seen, so therefore 1, 2, not 3, 4, this is not equals to 3, 4, not 1, 2. That means it is basically AB not CD, that is not equals to CD not AB. And that implies it is not commutative. So therefore, what we conclude? We conclude here is not is a commutative group. Is not is a commutative group. So this example gives us an example of a commutative group. And what we have seen in the first part, it is a group, but in the second part, we have seen this is not a commutative group because the commutative law does not hold here. Now we come to the next important question. Question number 7. And this question is asked in the year of 2009. So question is prove or disprove the set D of all integers, the set D of all integers forms a commutative group, forms a commutative group with respect to binary operation, star, and which is defined by A star B. This is A plus B minus 1 for AB belongs to D. So if we check that all the properties, that means closure, associative, identity and inverse, with the commutative law all are holds, then we can say it is a commutative group. So we come to the solution. Okay, first we'll check here what is our D. Our D set equals to set of all integers. And the binary operation star is defined by, and the binary operation star is defined by A star B. This is basically A plus B minus 1 for AB belongs to D. So what we'll check? First we'll check the closure property holds or not closure. So take any two element. Take any two element AB belongs to D. Then if we A star B, that will be A plus B minus 1. And this must be belongs to D. Why? Because A belongs to D, why D is integer, and B belongs to also D. So A plus B must be integer. So that means A plus B minus 1, that is also integer. So that must be belongs to D. So what we have seen here, sorry, here the question was D with the set of all odd integer. So D is the set of all odd integer. So we'll check A belongs to D, B belongs to D. So that means A is odd. A equals in the form of 2k plus 1, and B is also in the form of 2k 2 plus 1, because or where for some k1 k2 belongs to Z integer. So in that case, A plus B minus 1, that will be 2k1 plus 1 plus 2k2 plus 1 minus 1. That means it will be 2 into k1 plus k2 plus 1. This is also an odd integer. Okay, this is an odd integer. Odd integer. So obviously A star B must be belongs to D. So therefore this star B belongs to D for all AB belongs to D, because AB was arbitrary. So that means closure property holds. Now we'll come to the associative property. We know associativity holds in the in integer, and by the hereditary property we can say this is associative. So associative, I will check let A comma B comma C belongs to D. Then first we will calculate a star B star C, that will be A plus B minus 1 star C, and it will be A plus B minus 1 plus C minus 1. So what will be the value here? A plus B plus C minus 2. And if we calculate a star B star C, so that will be A star B plus C minus 1. That will be A plus B plus C minus 1 minus 1. And that will be again A plus B plus C minus 2. So therefore, here star B star C, that is equal to A star B star C for all ABC belongs to ABC belongs to D. So that means D is associative with respect to star. So now we come to the next. We check the existence of identity. It has identity or not. So clearly what we can say, 1 is an odd integer, so 1 belongs to D. Since 1 is an odd integer. And we see that 1 star A, that means 1 plus A minus 1. Again it will be A. And A star 1, that will be A plus 1 minus 1. Again it will be A. So therefore, what we see, 1 star A equals to A star 1. This is equals to A for all A belongs to D. Okay, and that is holds, okay, for A belongs to D. And since A is arbitrary, so that means this relation holds, and hence what we can conclude, hence 1 is the identity element, in the set of odd integers. Now we come to the existence of inverse. So now we'll check the existence of inverse. So here inverse, let A belongs to D. So then A is an odd integer. Okay. So now what we'll check here. So since A is odd integer, and from that we can write 2 minus A. This is also an odd integer. Why? Because since A is odd, so A we can write is 2k plus 1 for some k belongs to Z. And now 2 minus A, that means 2 minus 2k plus 1. So it will be 2 into 1 minus k, and into 1 minus k minus 1. That we can write 2 into, if we add here 2 and again we will take minus 2, so that we can write 2 into 2 minus k 2 into minus k, 2 into minus k, if I take common here 2 plus 1, that we can write. So this is also an odd integer. So now we see that a star 2 minus a. So that means a plus 2 minus a minus 1. And that will be 1. And again you will check 2 minus a star a. That will be 2 minus a plus a minus 1. Again it will be 1. So what is happening here? A star 2 minus a. This is equals to 1 and that equals to 2 minus a star a. And that holds for all a belongs to D. And since a belongs to D is arbitrary. And while 2 minus a is also belongs to, here 2 minus a belongs to D as it is an odd integer. So therefore, every element in D must have an inverse in D. So that means what we can conclude here, D with this operation star is a group. Now we'll check it is commutative group or not. So we'll check the commutative property. So we'll take commutative or not. So what we will do, we'll take two elements, AB belongs to D, and we'll check A star B equals to B star A or not. So now, what should be a star B? Star B will be A plus B minus 1. And what will be the B star A? B star A will be B plus A minus 1. Now, since we know A plus B minus 1 for integer, that is exactly equal to B plus A minus 1. Since A comma B both are integer. Okay? Because as Z as D is a subset of Z. And Z plus is commutative. So obviously from that we can write A star B equals to B star A. So what we have shown here, A star B equals to B star A for all AB belongs to D. So thus now we can conclude D with this operation star is a commutative group. Because it satisfies all the properties closure, associative, identity, inverse, and with the commutative law. So obviously yes, the group is commutative. That answer we can write here. Yes, the statement is true and it is commutative. Yes, the set D of all odd integers forms a commutative group with respect to the binary operation star defined by A star B equals to A plus B minus 1 for AB belongs to D. And this is our justification. We have checked all the properties. Now we come to the next important problem. Here the problem is true or false. This is question number 8. Question 8, and this question asked in the year of 2000. What was the question? True or false? True or false? In a group G0, if A not B equals to A not C, then B equals to C. This is asked for 2. That means here it is basically the left cancellation law. It is asked the left cancellation law holds or not. Okay. So how to give the answer? So we'll see the in a group we know the left cancellation holds. So obviously the statement is true. But okay, we need to prove why this statement is true. So we'll set up the justification why it is true. Okay. So obviously it is true because this law is basically called the left cancellation. Okay. So you know the left cancellation law. Left cancellation law. This is basically in a group G naught A naught B equals to A naught C. That implies B equals to C. There is also another important cancellation law. This is the right cancellation law. Right cancellation law. What is this? In a group G naught A naught B equals to say C naught B, that implies A equals to C. This is called the right cancellation. In group, both the cancellation law holds. Okay. So here, what is given? Here, G naught is a group. G naught is a group. Okay. And it also given, and it is given A naught B equals to A naught C. Okay. While A, B, C, this holds in G naught. This is given. So let us assume that let E be the identity element. E be the identity element in G. Okay, so this is our group G, where we have seen A naught B equals to A naught C. So all A, B, C are element of G. Now, what we assume, say since A belongs to G and G is a group, so that implies A inverse must be belongs to G. Now, what is given? A naught B equals to A naught C is given. So that implies A inverse not A naught B equals to A inverse not A naught C. Now, you know in a group, the associativity law holds. So A inverse not A not B, this will be A inverse not A not C. And from that we can write E not B equals to E not C. From that we can write B equals to C. Okay. So we have proved here A not B, A not C equals, that implies, therefore what we have proved, A not B equals to A not C, that implies B equals to C in the group G naught. Now we come to the next important question, question number 9, and this question asked in the year of 2002 as well as the 2008. Okay, so what was the question paper? True or false? The identity element is the only idempotent element. The identity element is the only idempotent element, only idempotent element in a group. And this is basically again for 2 marks question. So you need to justify it is true or false. That we will justify here. So now we need to know what is the definition of the idempotent element in a group, and then we will solve the problem. Okay. So we'll come to the solution. Before solution, we will recall some basic facts. So the fact is here, idempotent element in a group. Idempotent element in a group. Not saying identity. Idempotent element in a group, G naught. So here, still consider it is a group and is an element. So an element A belongs to G is called idempotent if A square equals to A. That relation holds. Then it will be idempotent element. Okay. So now we come to the problem, come to the solution. Yes, the statement is true. The statement is true. That means in a group, identity element is the idempotent element. Okay. So we need justification why it is the statement is true. So first we see that let E be the identity element in G. Identity element in the group G. I said group. It must have identity element. So our observation, we see that if we think about square, that means E into E, and that will be E. So that means that implies E square equals to E. So E is identity, E is idempotent. Idempotent element in G. That we prove. But we need to show that there exists no other idempotent element. So let A belongs to G, be an idempotent element. So first we have seen here is the idempotent element, but okay, then we will check if we take another element as an idempotent element, that will be again E. That means E will be the only idempotent element. So here it is given only. Okay, so you need to justify only. That means obviously will be the idempotent and is the only. There is no other idempotent element. So I take A belongs to even idempotent element. Then what we can write? Then we can write E square equals to A. Okay. Now since A belongs to G, that implies G is a group. That implies A inverse belongs to G. As G is a group, group means every element must have an inverse. So from that we can write here A not A equals to A, and that means we just multiply A inverse on both sides. This is A inverse not A. Just I consider not is an operation. So from that we can write, okay, so A inverse not A, by associativity law, that will be A inverse not A. Is the idempotent, is the identity element, so inverse not A, that means E not A equals to E. That means again A equals to E. So if we take any arbitrary element A as an idempotent, then again that A will be E. So that means, therefore, what we conclude, the identity element is the identity element E is the only idempotent element. Is the only idempotent element in G. So that means the statement is true. Now we'll come to the next important question. The question is question number 10. And this question has been asked in the year of 2009. Let G star be a group and A comma B belongs to G. Suppose that A square equals to E, and A star B star A, this is equals to B to the power 7. So prove that B to the power 48 equals to E, where E is the identity element in G, where E is the identity element in G. So now we will come to the solution. What is exactly given? It is given G with this operation. This is a group. This is given. And it is also given A comma B belongs to G. And it is also given A square equals to the identity element, and A star B star A, this is B to the power 7. What we have to prove? We have to, here it is given A square equals to E, and A star B star A, this is equals to B to the power 7. What we have to prove? We have to prove that B to the power 48 equals to the identity element. It is E is basically the identity element, where E is the identity element in G. Okay, so that we have to prove. The question is how to prove. How to prove? So here we have A star B star A. This is basically B to the power 7. We need to increase the power of B. So from that, we just raising the 7th power. So A star B star A 7, B 7 to the power 7. And that will be B to the power 49. And using associativity, what we can write? A star B star A star A star B star A star A star B star A star B star A. This is basically 7 times. 7 times. And that is will be B to the power 49. That we can write A star B star A star A star B again A star A star B again A star A and star B star A. Just we apply the associativity. And associativity holds. Now you know the square, A star means square. So that will be A star B to the power 7 star A. This will be B to the power 49. Why? Because A square equals to A is given. The identity element in G. Identity element in G, and you know A star A means A square, and this is basically E. It is given. So what we get here? So again, so what we get? We get here A star B to the power 7 star A. This is equals to B to the power 49. Now you know it is given B to the power 7 is A star B star A. This is given. So just we'll put the value here is star here star A. This is equals to B to the power 49. So in position of B to the power 7, what we will write? A star B star A. So this is given here. So now again by associative law it will be A star B star A star A. This will be B to the power 49 because of by associative law. By associativity. Again this will be A square star B star square, that will be B to the power 49, and again it will be E star B star E, that will be B to the power 49. Since it is given square equals to identity, so it will be B equals to B to the power 49. And that we can write B star E equals to B star B to the power 48. Now by the help of cancellation law, we know the left cancellation holds. That means E equals to B to the power 48. Because since B belongs to G and hence B inverse, that implies B inverse belongs to G. As G is a group. G is a group. And in that case we can write B inverse star B star E equals to B inverse star B star B to the power 48, and that implies B inverse star B star E equals to B inverse star B star B to the power 48 by associativity. So what we get? B to the power 48 equals to identity. Okay, and this is proved here. So we have proved B to the power 48 equals to identity. Now we will come to the concept of abelian group. Abelian group. Abelian group. So what is our recall here? Our recall is a group that is said earlier. Say G naught is called abelian. Is called abelian group if and only if A naught B equals to B naught A holds for all AB belongs to G. Okay? If this relation holds. Group is already there, but we need to satisfy the abelian property, then it will be abelian group. So here the question is basically question number 10, question number 11. That will be question number 11. And this question has been asked in the year of 2097, 2001 and 5. The question in a group G, if A equals to A inverse for all A belongs to G, then prove that G is commutative group or G is abelian group. The same name, commutative group. The question is the converse true? Is the converse true? Justify your answer. Justify your answer, and this question is basically for 3 marks. Now the thing is how to solve this question. What is exactly given and what we'll do, that we need to consider first. So it is given, the first is information G is a group. And there some certain operation with the composition or not. And what is given? A equals to A inverse for all A belongs to G. And it is also given A equals to self inverse. Every element is its self inverse. Then we need to show G is a commutative group. So what we have to show, or we have to prove that G is commutative. G is commutative group. So group is already there. So just we will check the commutativity property. It is commutative or not. And from that we can show it is a commutative group. So we'll take two elements xy. Let x comma y belongs to G. What we have to show? We have to show here xy equals to yx for all xy belongs to G. That we have to show. Okay, this is our target. So since xy belongs to G, then we can say xy belongs to G. As since G is a group, so closure property holds. Closure property holds. This is the first property to be a group. So xy must be belongs to G. What is the property for all element in G? A equals to A inverse. So from that, what we can say, so by the given condition, we can say xy equals to xy inverse. Why? Because it is given A equals to A inverse for all A belongs to G, and what we have seen, xy belongs to G. So xy equals to xy inverse. And from that, what we can write? From that, we can write xy equals to y inverse x inverse. Why? Because since in a group G, AB whole inverse must be B inverse A inverse for all AB belongs to G. Okay, this is a property of a group, standard property. So now since x, y both belongs to G, so that implies x equals to x inverse and y equals to y inverse. Why? Because it is given that A equals to A inverse for all A. That property is given. So by the given property we can write. So therefore, 1, this is 2. Therefore, from 1 and 2, we get what is xy equals to y inverse. Y inverse we can write y, and x inverse we can write x. And since x inverse equals to x and y inverse equals to y. So since x is arbitrary, so what we can say, x equals to yx for all xy belongs to G. And hence, our conclusion is G is a commutative group. Because it satisfies the commutative law and group is already there. So G is a commutative group. So if in a group you will see every element is its own inverse, so then that group must be commutative. Now is the converse true? So converse part. Is the converse true? Our answer is that you can consider as the second part of this question paper. Second part. So here it is first part of the first part. Okay, so in the second part, is the converse true? Our answer is no. The converse is not true. No. The converse is not true. Okay. How? Consider the Z plus. Consider the group Z plus, which is commutative. Commutative group. But what we have seen, we see that one, this is not equals to 1 inverse. That means minus 1. Because in Z plus, if we take any element, Z plus, n inverse will be minus n for all n belongs to Z. Okay. So here 1 not equals to 1 inverse. So that means the converse is not true. So that is not holds in each group. Okay. But in a group, if holds every element is its own inverse, then the result will be valid. Now the question is question number 12, and this question asked in 1998. Prove that a group is commutative if and only if a group is commutative if and only if and only if AB whole inverse this will be A inverse B inverse for all AB belongs to G. Okay. Now question is how to solve. So first we will consider G is commutative and we will show AB whole inverse equals to A inverse. So let G is commutative group, and from that we show that AB whole inverse equals to A inverse B inverse for all AB belongs to G. That will be our first. We can consider that condition, and from that we will show that G is the group is commutative. Okay. So what will take? Any two elements AB belongs to G. Okay. Then AB whole inverse by standard property we can write is B inverse A inverse. Okay. Because since in a group G XY whole inverse, that will be always Y inverse X inverse for all. This is standard property of a group. And from that, because it is a commutative, since G is commutative and B inverse belongs to G and A inverse an element of G, because G is a group. So both inverse exist, as A comma belongs to G and G is a group. So obviously we can write it A inverse B inverse. So what we have proved here, therefore AB whole inverse equals to A inverse B inverse. And since AB belongs to G is arbitrary, so AB whole inverse we can write A inverse B inverse for all AB belongs to G. Why? Because A comma B belongs to G, that are arbitrary element. So now we come to the second point, the converse part. That means it is given. Okay, so we'll do the reverse. Conversely, let in the group G naught AB whole inverse, this will be A inverse B inverse for all AB belongs to G. What we have to show? We have to show that G is a commutative group. G is a commutative group. That we have to show. Now how to show it? So what we will do, we'll take, so this is your G, we'll take any two element AB and we'll show AB equals to BA for all AB belongs to G. Then G will be commutative. So we'll take the AB are element of G. Okay. Then by the given condition, what we'll write? We'll write AB whole inverse equals to A inverse B inverse. That we can write. because it is given here. So you can write by star. So now if we multiply both sides by AB, and from that we can write here AB whole inverse, that will be AB A inverse B inverse. From that we can write that will be identity E AB A inverse B inverse. Why? Because since X inverse equals to identity for all X belongs to G, where E is the identity in G. Okay? And from this we can write by associative law AB A inverse B inverse equals to E by associativity. And that implies AB A inverse equals to B. And here you can write AB A inverse A equals to BA. You see, multiple both sides by A. And from that we can write AB A inverse A equals to BA. Again by associativity. And from that we can write AB E equals to BA. And from that we can write AB equals to BA. So what we have seen, AB equals to BA for all AB belongs to G, because all AB was arbitrary. Hence, G is, initially it was group, now commutative property holds, so G is a commutative group. So here we have proved this problem. So a group is commutative if and only if AB whole inverse equals to A inverse B inverse. Now we come to next problem. Okay, so in the next class we will do the next 3 problems and we will continue again 3. So thank you so much.